Welcome to AES Encryption. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we're going to explore AES encryption in simple, everyday terms. AES stands for Advanced Encryption Standard, and it's like the Fort Knox of digital security. Imagine you have a secret diary that you want to keep private. In the old days, you might have used a simple lock and key. AES is like having a super sophisticated lock that would take even the world's best lockpickers billions of years to break. AES is everywhere in our digital lives. When you shop online, check your bank account, or send a WhatsApp message, AES is working behind the scenes to keep your information safe. It is the encryption standard chosen by the US government and used by organizations worldwide. Think of encryption as a way to scramble your information so that only someone with the right key can unscramble it. It's like taking a completed jigsaw puzzle, mixing up all the pieces in a very specific way, and only giving the instructions to put it back together to someone you trust. Understanding encryption basics. Before we dive into AES specifically, let's understand what encryption really means. Imagine you're passing notes in class. Remember doing that? You don't want the teacher to read your note if they intercept it. So you and your friend agree on a secret code. Maybe A becomes Z, B becomes Y, and so on. That's a very simple form of encryption. In the digital world, encryption works similarly but with much more complexity. Your original message is called plaintext. That's the readable version. The scrambled version is called ciphertext. That's what looks like gibberish to anyone who doesn't have the key. The process of scrambling is encryption, and unscrambling is decryption. The diagram on the slide shows this flow. You start with your plaintext message, like "Hello world." You apply an encryption algorithm, the set of rules for scrambling, along with a secret key, like a password. Out comes the ciphertext, something that looks like random characters. To read the message again, you reverse the process with the same key. What makes modern encryption like AES special is that even if someone knows exactly how the encryption works, they still can't break it without the key. It's like knowing exactly how a lock works but still not being able to open it without the right key. What makes AES special? AES didn't just appear out of nowhere. In the late 1990s, the US government realized they needed a new encryption standard. The old one, called DES, was becoming vulnerable as computers got faster. They held a competition, and cryptographers from around the world submitted their best designs. After years of testing and analysis, an algorithm called Reindahl, pronounced Reindahl, created by two Belgian cryptographers, was chosen and became AES. What makes AES so special? First, it is incredibly secure. We are talking about security that would require more computing power than currently exists on Earth to break. Second, it is fast and efficient. Unlike some encryption methods that are secure but slow, AES can encrypt and decrypt data quickly, making it practical for everyday use. Third, it is versatile. AES can work with different key sizes, 128, 192, or 256 bits. Think of these as different sizes of locks. For example, a 128-bit key has so many possible combinations that the number is difficult to comprehend. The 256-bit version is exponentially more secure. Finally, AES is transparent. The algorithm is public, meaning security experts worldwide can examine it for weaknesses. This openness, paradoxically, makes it more secure because thousands of brilliant minds have tried to break it and failed. How AES works. The safe analogy. Let me explain how AES works using an analogy everyone can understand. A super secure safe. Imagine you have a valuable document you want to protect. With AES, you are not just putting it in one safe. You are putting it through a series of transformations that would make a magician jealous. First, your document, the data, is divided into blocks of 128 bits each. Imagine this as cutting your document into standard-sized pieces that fit perfectly into our encryption machine. Each piece then undergoes the same process independently. Now, here's where the magic happens. Each block goes through multiple rounds of transformation. For AES 128, it's 10 rounds. For AES 192, it's 12 rounds. And for AES 256, it's 14 rounds. Each round is like putting your document through a different security procedure. In each round, 4 things happen. First, each byte of data gets substituted with another byte according to a special table, like replacing each word in your document with a code word. Second, the rows of data get shifted. Imagine sliding rows of text in different directions. Third, the columns get mixed up using mathematical operations, like scrambling vertical columns of letters. Finally, a piece of the key gets mixed in, like adding a unique security stamp. After all these rounds, your original data is so thoroughly scrambled that it's practically impossible to reverse without the key. It's like your document went through a shredder. The shreds were rearranged, painted different colors, mixed with other materials, and then reassembled in a completely different pattern. AES key sizes explained. When we talk about AES key sizes, we are essentially talking about the length of the password that protects your data. But these are not your typical passwords. They are incredibly long strings of bits, ones and zeros, that determine exactly how your data gets scrambled. AES 128 uses a 128-bit key. To put this in perspective, if you tried to guess this key by trying every possible combination, and you could try 1 billion keys per second, it would take about 5 billion years. That's many times longer than the age of the universe. AES 192 uses a 192-bit key, which increases the security exponentially. Each additional bit doubles the number of possible keys. So, going from 128 to 192 bits does not just add 50% more security. It multiplies the difficulty by an astronomical amount. AES 256, the strongest variant, uses a 256-bit key. This is often called military-grade encryption because it is what governments use for top-secret information. The number of possible keys is so large that if you turned every atom in the universe into a computer, and they all worked together trying keys, they still could not crack it in any reasonable timeframe. So why doesn't everyone just use AES 256? Well, stronger encryption requires more processing power. For most purposes, AES 128 is more than sufficient. It's like asking why not everyone drives a tank. Sometimes a regular car with good locks is perfectly adequate for your needs. Real-world applications. AES is like the invisible superhero of the digital world. It is everywhere, protecting us, but we rarely notice it. Let me walk you through some everyday scenarios where AES is hard at work. When you connect to a website that starts with HTTPS, which is indicated by the little padlock icon in your browser, AES is often the encryption protecting your connection. Every time you enter your credit card information to buy something online, AES ensures that hackers can't intercept and read your card number as it travels across the internet. Your smartphone is another AES powerhouse. When you set a passcode or use your fingerprint to lock your phone, AES encrypts all the data stored on it. This means if someone steals your phone, they cannot just plug it into a computer and read all your photos, messages, and apps. The data is scrambled beyond recognition without your passcode. Wi-Fi networks use AES too. When you connect to a password-protected Wi-Fi network, AES encrypts the data flowing between your device and the router. This prevents your neighbors or anyone nearby from snooping on what websites you're visiting or stealing your passwords. Even messaging apps like WhatsApp, Signal, and iMessage use AES to implement end-to-end encryption. Your messages are encrypted on your phone with a key that only the recipient has. Not even the company running the service can read your messages. They just see encrypted gibberish passing through their servers. File storage services like Dropbox, Google Drive, and iCloud also use AES to protect your files. When you upload a document, it gets encrypted before being stored on their servers. This ensures that even if hackers somehow broke into these companies' data centers, they couldn't read your files. AES security. Why it is unbreakable. When I say AES is unbreakable, I mean it in practical terms. Theoretically, any encryption can be broken given enough time and resources, but with AES, we're talking about timescales and resources that are simply impossible in our physical universe. Let's look at the numbers. A brute force attack means trying every possible key until you find the right one. For AES 128, there are 2 to the power of 128 possible keys. That's approximately 340 undecillion different keys to try. If you had a computer that could try 1 trillion keys per second, it would take about 10.79 sextillion years to try them all. The universe is only about 13.8 billion years old. But what about quantum computers? You might have heard they could break encryption. While quantum computers do pose a theoretical threat to some types of encryption, AES is relatively resistant. Even with a quantum computer, AES 128 would still provide 64-bit security, which is still very strong. And AES 256 would provide 128-bit security, which is still far beyond what is practically breakable. The diagram shows different attack timescales. Notice how even with massive computational resources, like harnessing the power of every computer on Earth, breaking AES would still take longer than the heat death of the universe. This isn't just very secure, it's secure beyond the limits of physical possibility. It's worth noting that when AES systems are compromised, it's never because someone broke the encryption itself. It's always due to other factors, such as weak passwords, software bugs, social engineering, or implementation flaws. The algorithm itself remains unbroken after more than 20 years of scrutiny by the world's best cryptographers. Common misconceptions. There are many myths and misunderstandings about AES encryption that I'd like to clear up. Understanding these will help you make better decisions about your digital security. First, military-grade encryption. You see this term everywhere in marketing. The truth is, AES 256 is indeed used by militaries, but it is also used by your iPhone and your bank. The term military grade is more marketing than meaningful distinction. AES 128 is already incredibly secure for most purposes. Second, many people think more encryption rounds or bigger keys always means better security. While AES 256 is theoretically stronger than AES 128, both are so far beyond what is breakable that for most users, the difference is academic. It is like debating whether a steel door that takes 1,000,000 years to break through is better than one that takes 1,000,000,000 years. Both are effectively impenetrable. Third, some believe that if the algorithm is public, it must be less secure. This is completely backwards. The fact that AES is open and has been studied by thousands of experts makes it more secure, not less. Security through obscurity, hiding how something works, is actually a sign of weak security. Strong encryption like AES remains secure even when the attacker knows everything about how it works except the key. Finally, there is a misconception that encryption significantly slows down your devices. Modern processors often have special instructions built in specifically for AES encryption. Your phone can encrypt and decrypt data so quickly that you do not even notice it is happening. The performance impact is negligible for most applications. Simple Python AES example. Let me show you how simple it is to use AES encryption in practice. Don't worry if you're not a programmer. I'll explain each line in plain English. This example uses Python, one of the most beginner-friendly programming languages. First, we import the necessary tools. Think of this like getting the right tools out of your toolbox before starting a project. The cryptography library is a well-tested, secure implementation of AES that handles all the complex mathematics for us. Next, we generate a random key. This is crucial. Your key should always be random. not something like password 123. The OS.U random 32 function asks your operating system for 32 random bytes, which gives us a 256-bit key. It's like asking a quantum random number generator for the most unpredictable key possible. We also need something called an initialization vector, or IV. This is like adding salt to your cooking. It ensures that even if you encrypt the same message twice with the same key, you get different ciphertext each time. This prevents attackers from noticing patterns. The encryption process creates a cipher object. Think of it as setting up your encryption machine with your specific key and IV. Then we call the encrypt method with our message. You will notice that the encrypted output looks like random garbage. That is exactly what we want. Decryption is just the reverse process. We set up the cipher object the same way, but call decrypt instead. Out comes our original message, perfectly preserved. The beauty is that without that key, the encrypted data might as well be random noise. Best practices and summary. As we wrap up our journey through AES encryption, let me leave you with some practical advice for using encryption in your daily life. First and most importantly, use strong, random keys. The best encryption in the world won't help if your key is password or. Use password managers that can generate and store strong random keys for you. Think of it this way. Having AES encryption with a weak password is like having a bank vault door on a house made of cardboard. Keep your keys secret and separate from your encrypted data. Storing your key with your encrypted data is like taping your house key to your front door. Use secure key management practices, whether that's a password manager for personal use or dedicated key management systems for business applications. Always use well-tested, standard implementations of AES. Do not try to modify the algorithm or implement it yourself, unless you are a cryptography expert. It is like performing surgery. Leave it to the professionals who know what they are doing. Stay updated with security patches. While AES itself remains secure, the software implementing it needs regular updates. Enable automatic updates on your devices to ensure you are protected against any discovered vulnerabilities. Remember, AES is a powerful tool for protecting your digital privacy. From your online banking to your personal messages, it's working tirelessly in the background. Understanding how it works helps you make informed decisions about your digital security. You don't need to be a cryptographer to benefit from AES. Just use services and devices that implement it properly, use strong passwords, and keep your software updated. Thank you for your attendance. Please consider subscribing to the channel.